And today's topic, if I can see the screen, is GLP-1s. So we've all heard of Ozempic and Wegovy and all these things. So, and we've all heard of, the lawsuits happening, the risks and all these things. I personally don't like them. I think a lot of people don't like them. But they are big profit makers. But it's very bright here, so I'm having to hold my hand up here. They make a lot of money. So it's a bit like, I think I mentioned it to someone the other day. I said it's a bit like, I'm not saying they're equivalent, and I'll explain this in a second, but it's a bit like smoking in the sense that, there was a time when even the FDA used to recommend smoking, if I'm not mistaken, and there were adverts where doctors used to say, this is the one I recommend, or there were taglines like the cigarette brand your doctor uses, something like that. And only after so many grassroots frontline cases and responses did people have to admit, okay, maybe this isn't so good for us. And then obviously everyone did a U-turn on it, and we see smoking as this bad thing now. My thought process is that maybe this is going to be like that. There's lots of money to be made, and lots of people say they're great, but maybe it's going to be a similar principle in terms of lots and lots of frontline grassroots cases where lots of bad things are happening. Lawsuits are already started to happen before people realize these things aren't as good as they seem, and they're not actually treating anything, as I'm about to hopefully show you. I'm just going to put these glasses on again, just so I can actually see the screen. There we go, and use my hand on the mouse. So I'm going to share my screen here. 1 second. It's very difficult to do with just words when you're going into quite deep biochemistry sometimes. So I've made a bit of a whiteboard. I pre-prepared this a few minutes ago, as you can tell, because it's very rudimentary. And if you imagine, what's going to happen in terms of when we take this drug as a story, I'm going to talk through it here on the screen in a sort of step-by-step pathway, like a story going from one place to another. So on the left-hand side, you can see this sticky label called ECM. This basically means extracellular matrix. So this is the area outside of the cell. And on the right-hand side, SMC means smooth, or stands for smooth muscle cell. So this band that you see running across, which I'll just draw on 1 second, all of that is the membrane. So everything on this side is the ICM, the intracellular matrix within the cell. You got the cell membrane, and then outside the cell here. So let's pretend we are about to add in a drug. We're about to add in this GLP-1 drug. Let's use this. Okay, let's get rid of that. Let's make it a different color. Okay. So this is what we've delivered. You've given the GLP-1 drug. Let me just label that. And this is Wegovy. Now, why have I chosen Wegovy specifically? Because in these classes of drugs, there are essentially 3 receptors we're talking about. There's GLP-1, there's GIP, and then GR, which is glucagon receptors as well, gastric inhibitory peptide, glucagon-like peptide. Now, depending on what you're talking about in terms of drugs, you're going to be going for one or a combination of these. So something like GLP-1, that is something like Wegovy, which hits that one receptor, which is what I've drawn on the right-hand side here, GLP-1R, GLP-1 receptor. GIP, this is, I've done this in this order because you've then got, type it in here, this will be easier. GLP-1 and GIP, this is going to be something like Mounjaro. And then you've got GLP-1, GIP, and GR. This is going to be the newer ones like Retatrutide, if I can spell it, there we go. So today, what I'm really going to talk about is this one here, the GLP, the GLP-1s. Now, in future calls, I am going to go through the others as well, just so you've got a full picture of absolutely everything. Now, what's happened when we've delivered this particular drug, the GLP-1, the Wegovy, is that this drug now is sitting in this sort of funnel shape here. And this is a receptor, and this is the GLP-1 receptor. It's a transmembrane receptor, so that means that, I can take my glasses off, the sun's gone out. It means that part of the receptor is outside and part of it is inside. So when something on the outside interacts with it, it basically has something called signal transduction, where something on the inside then happens as a result. So this is what we call receptor activation. And this is a G protein, this protein here. And so you've got what's called G protein coupling. And on the inside of the cell, on the inside of the cell, this is where you have what's called a GS protein. This is basically a stimulatory, that's what the S stands for, G protein. Now, if this is a little bit out of your depth in terms of your biochemistry, don't worry. As long as you understand the flow and the story and the pictorial version, you're in the right ballpark. So what happens is when we have signal transduction here, when Wegovy bounds to this GLP-1 receptor, this receptor then has an interaction in signal transduction with this G protein coupling, with this GS protein. Now what happens is this basically has two subunits. I've put it down as two cylinders here. So you've got beta, gamma, and alpha S. What happens is that these kind of just dissociate, right, into two separate units as opposed to one whole unit like this. And when they separate, when they dissociate, what you're seeing basically is the alpha S subunit come away and take part in a bit of activity. And that's what I'm going to show you here. So this alpha S, how do I get an arrow on this thing? Arrow, there we go. Oh, is that an arrow? Yeah. Okay. There we go. Let me zoom out of it. So that single subunit then has an interaction with this enzyme. Again, this is an enzyme that's embedded into the membrane, i.e. the cell membrane of this smooth muscle cell. And what adenylate cyclase does is it gets activated as a result of this subunit coming away. And like I said, it's in the plasma membrane, and here it converts something into something else. So I've not actually written that in. Let me do it now. So it converts ATP to CAMP, cyclic AMP. Now, what happens then as it, let me move this arrow out of the way. Once that happens, you've said this thing here, this section at the bottom is basically a loudspeaker or a megaphone. And this thing here is the microphone. So you've got a microphone here listening out for something, someone talking, which is Wegovy chirping up. And then you've got a wire into a speaker. And when the speaker is playing that sound, now that sound is much, much louder than when we heard it. So what this thing does here, this cyclic AMP, is kind of amplify the signal of this. So this is why this is seen as a signal amplifier in layman terms, if you like. So what happens now is that as this happens, I can drag this thing over here. There we go. The cyclic AMP increases, right? The concentration of that within the cell increases. This is now a secondary messenger. So this is carrying the voice, if you like, of this Wegovy drug, or this interaction, if you like, into the cell. So for example, you may have seen videos, and sorry to go off on a bit of a tangent, but I'm aware people will be watching this with no scientific understanding whatsoever, and I want to cater to everyone. You may have seen videos of cars being stolen from driveways, even without the key. And what happens is someone will hold up this weird hanger or antenna-like thing in front of the house, in front of the front door. And what that's doing is searching for the key signal in the house. And once it's got the key signal from one side, on the other side, it will spit it out much louder. So then the car will unlock itself. And that's how people can steal your car without even the key. And that's why you need to keep the key wrapped in foil or some kind of Faraday cage or some kind of box to, you know, to block its signal when you're not using it. That's very akin to this, right? So this adenylate cyclase, you know, it's looking for the key, which is here, the Wegovy, the binding to the GLP-1 receptor. And this is its antenna, the alpha S subunit. And that antenna has clocked the signal, and now it's playing that signal much louder to try and steal the car or to go into the cell, which is a cyclic AMP. Now, these levels rise very, very rapidly inside the cytoplasm of the cells, of these smooth muscle cells, following GLP-1 receptor activation. Once that activates, we've then got something else happening. Let me get an arrow. There we go. Whoops. Arrow, yep. And we go over here. Okay, let me leave it at that. So then the cyclic AMP, it can bind to the, let me just write this here. So that's an R. So the cyclic AMP binds to the regulatory subunit of pKa. So this big section here, the top bit, is what we call the regulatory unit. And this thing is protein kinase A, very creatively named, as you can tell, all these things. So protein kinase A, and it's binding to the regulatory subunit. Once it binds to the regulatory subunit, it's a bit like, I haven't seen the film, but I have seen clips of it. It's a bit like in one of those Avengers films where there's like this big alien that comes into New York or wherever it is, and it's like a big slug. And then when it tries to kill everyone, it releases all these mini slugs that come away, like little soldiers coming off from the main ship. Or if you like, when someone's abandoning a big boat, they come away in lifeboats. So it's a similar principle in terms of what I'm trying to show here. So you have these basically coming away. So it releases these other units. And what's happening is these are the catalytic subunits. So you've got the regulatory subunit here, and then you've got the catalytic subunit over here. So when it binds to the regulatory unit, the catalytic bits basically release. And this is then activated, protein kinase A. And activation of protein kinase A is really where the effect of these GLP-1 agonists are seen. At that point, you start to figure out how this drug actually works, in this case, Wegovy. This then has an interaction with other areas. So what this does is it phosphorylates certain proteins, which are its targets. Now, as a result of this, basically reduces the calcium. Now, this notation here, whenever you see something in chemistry in square brackets, it means concentration. So here it means concentration of Ca2+, so a calcium ion. If it was elemental calcium, it would just be Ca. And the I basically means intracellular. So it's reducing the concentration of intracellular calcium 2+ ions. That's a shorthand way of saying it. Now, this is required for muscle contraction. We need calcium to contract our muscles, not just the smooth muscle, which is involuntary in the digestive tract, but even skeletal muscle under voluntary movement as well. Calcium is in every cell of our body. It's incredibly useful. In fact, not just useful, it's essential, I would say. And it modulates so many functions within the cell. So anytime you're taking something which plays, shall we say, with the calcium, you've got to really ask yourself, what is actually going on here? Is this really a good thing to interfere with something so crucial everywhere? So let's have a look at what kind of things it does. So we've got a few little boxes here. Let me just draw an arrow. So the first thing, this is not in any particular order, by the way, but the first thing is it mediates the phosphorylation of MLCK, so myosin light chain kinase. Now I'll break that down for you. A kinase, or anything with an ASE, is an enzyme, like amylase breaks down starch, lactase breaks down lactose, a kinase is an enzyme. A kinase means you add a tag onto a target molecule. That tag is a phosphate, okay? So if you have something like AMP kinase, you are adding phosphate onto AMP, adenosine monophosphate. That could go to adenosine diphosphate. If a kinase then phosphorylates that, it can go to adenosine triphosphate, etc., and so on. So myosin is a part of the muscle. It's one of the chains that makes up muscle fibers, if you like. And light chain tells us, which chain it is. So it's basically saying it phosphorylates an enzyme that adds a phosphate group onto a part of our muscle. And that is not good. Okay, you may think, well, so what? If you phosphorylate this enzyme, what that means is that in your muscle, the two fibers, the two proteins, I should say, actin and myosin, they cannot form a cross bridge. What does that mean? It means your muscle can't contract. When we're talking about muscle contracting, we're talking about actin and myosin binding together, a bit like two people shaking hands. They're crossing over each other. And that contraction is what shortens the length of the muscle, and that we then call a contraction. So essentially, straight away, we're seeing how it stops the muscle contraction. And remember, if we scroll back a little bit, we're talking about smooth muscle cells. What is a smooth muscle? Smooth muscle is an involuntary muscle. It takes part in things like our vasculature, so that it can automatically relax or contract to change the diameter of our blood vessels to increase or decrease blood pressure as we see fit. In this particular case, we're talking about the digestive tract. So what is smooth muscle doing in the digestive tract? Well, it's helping push the food through in a process called peristalsis. Peristalsis is just a technical way of saying a snake-like movement where a bolus of food is traveling through this tube, this digestive tract that we have, our intestine. So automatically you have to ask, okay, so it's working by stopping our cells from working. It's working by stopping our cells from doing the thing that is required to keep us alive. It is stopping our cells from doing exactly what they are designed to do, right? So what happens if they can't do that? Well, in essence, take this with a pinch of salt. I'm trying to use layman's terms here, but you're basically killing your intestines, as far as I'm concerned, at the very least. And all this biochemistry, you can't tell me I'm wrong on this. We just know this is how it works. So let's move down the list. Let's draw another arrow here. It activates something called MLC phosphatase, a myosin light chain phosphatase. This is another enzyme, ASE. So what this means is this myosin light chain that we have here, that is dephosphorylated, i.e., it can't be phosphorylated because this is inhibited, and any existing phosphorylation is taken away. So therefore, you've got even more inhibition with actin and myosin interaction. So even more, you're reducing the muscle contraction, you're reducing peristalsis, you're reducing the entire point of the cell, its entire function. What else? We now have an inactivation of calcium channels, which means we're basically locking the door that calcium has to go through to come into the cell. Therefore, calcium can't come in. We've locked the door and we've put the key, we've left the key in the lock, so no one can put their key in from the other side to unlock it. So now we've stopped the muscle contraction. We've stopped calcium coming into the cell. Let's go on to the next point, if I can draw an arrow. There we go. And we are also activating, K is potassium, crucium, I think it is in Latin, activates potassium channels. So therefore, and if you remember this notation here, we have an increase in the intracellular concentration, square brackets, of K plus potassium ions. So what if potassium comes in? Well, if potassium comes in, that muscle cell is now hyperpolarized, which means it's not very easy to excite the cell, i.e. to turn it on, if you like. And that means less calcium entry as a result, of this little pathway that we've got here. So 2 counts, calcium cannot get into the cell. 2 counts, the muscle cannot actually work. Then we've got something else. We've got this section here, which shows us that any existing calcium in the dissolvable part of the cell, which is the cytoplasm, or the cytosol, I should say, any calcium in the cytoplasm, it gets buried away into a cupboard, like as if you can't bother to clean something up, so you just put the rubbish in a cupboard and then clean it up afterwards after that person's left. So we have an increase in the activity of SERCA, which is sarcoplasmic endoplasmic reticulum calcium ATPase, also known as SERCA. So this takes the calcium and puts it into the sarcoplasmic reticulum. Now, if you don't know what the sarcoplasmic reticulum is, I'll just draw. It's basically another part of the cell. It's just a sequence of structures where things happen. I won't go into it in too much detail, but just like the nucleus is a part of the cell, the mitochondria are a part of the cell, the endoplasmic reticulum is just another part of the cell. That's it. And there's spaces in between. So what's happening is they are taking the calcium. Can I take it? Let's put Ca plus. Let's make it that color, seeing as it burns with the color. So what this is doing is taking this calcium, and in fact, let me draw an arrow like this, and it is putting it inside these things. So it's going from in the intracellular matrix inside the endoplasmic reticulum. So now the actual part of the cell, the body of the cell, the cytoplasm, even less. So 2 counts, we've got muscle contraction stopping or being inhibited. 2 counts, we've got the inability of calcium to now enter the cell like before. And 1 count, it's like charges of a lawyer in court, isn't it? 1 count of moving the calcium into the endoplasmic reticulum. Now remember, calcium's crucial for controlling cell function, not muscle contraction, cell function. And we are decimating the intracellular concentration of this thing. Now, there's another thing as well, which I won't go into in massive detail, but I want you to just be aware of it. At the bottom of the screen, you can see cyclic AMP is also involved in something called an EPAC pathway. That's something where it can activate RAP1, a small GTPase. I'm not going to go into that in detail today, but I will say that modulates the kind of the cytoskeletal dynamic of the cell, which is the skeleton of the cell, which gives it its something, the scaffolding to keep it in its particular shape. So it interacts with that as well. Now it's less dominant than the pathway I've shown here. And then it's also working by this thing called NO crosstalk, nitric oxide crosstalk. So in some tissues of our gastrointestinal tissue, in some of our gastrointestinal tissues, the CAMP, the cyclic AMP, may actually enhance the release of the nitric oxide from certain enteric nerve cells, like neurons, or even smooth muscle cells. And that then ultimately has another end, shall we say, of inhibiting the calcium signaling. So these two are also happening at the same time because they're not as dominant as what we're seeing here in the PKA pathway. I've not put too much effort into it, but it's there and I'm just skipping it, essentially. So what happens when these 5 boxes actually take place within the cell? So we have this, what I would class as a dangerous trifecta. So we have reduced peristalsis. So peristalsis is like, if you imagine, so let me draw it here. If you imagine this is someone's face, and then that's their neck, that's their mouth, nose, eyes, etc. This is obviously an alien, as you can tell. So if they eat some food, what will happen is, in a cartoon, let's say, the neck has a bulge there and there, and as they swallow, this bulge goes down. So what's happening to create that is that you have muscle going down, contracting one after the other to squeeze the whole thing along. Just like you're trying to squeeze something out of a tube, the end of a toothpaste, if you like. And this one by one contraction, which in a cartoon shows this bulge going down, just like food goes through our intestine, that movement is called peristalsis. So we have a reduction in peristalsis. And this essentially just slows down the way we break down our food. Now think about it very critically. If we can't break down our food very well, how are we going to nourish our own bodies? I'll let you be the answerer of that, if you like. Then we've got the relaxation of the pyloric sphincter. So a sphincter muscle is like a round, ring-shaped muscle. So we've got, we've got an anal sphincter, we've got a sphincter in the stomach as well. And if the sphincter in the stomach is not very good and acid is allowed to go through, we have gastroesophageal reflux. We have acid reflux, if you like. Now, this regulates the passage of things into the duodenum, which is part of our digestive tract, and essentially it just remains relaxed, or it just opens less often, less frequently, which delays the rate at which we empty our stomach, i.e. delays gastric emptying. You may have heard that phrase very often, delays gastric emptying. They talk about that as being the mechanism of action of these drugs. Yes, it delays gastric emptying, just like I would delay your ability to finish the marathon by chopping one of your legs off. Doesn't mean it's good for you. You have to ask why, how, what is the mechanism of action of this thing? And as you can see, it's not necessarily good. And then we have essentially the feeling of being full. That's amplified. We have prolonged gastric distension. So the stomach retains that food for much, much longer, which is why you feel full. And it's doing that via vagal afferent nerve fibers, and that contributes to, as I say, as I've written here, the satiety, and therefore the, shall we say, the appetite suppressing effects of GLP-1 drugs. Now, this is why, we talk about this thing here, this reduced peristalsis, pyloric sphincter relaxation. We could probably do it like this, in fact. If I move this arrow over there, and then draw another arrow there, that's kind of the way it should be, if you like. Now, these things here, this is why there are cases where people's intestines, and I'm being layman here, but people's intestines have basically just died. Like, if I'm not mistaken, there are people who have had to have colostomy bags because of the way these drugs actually work. Now, I'm just going to come back. I'm going to stop sharing this for a second and come back, because we've kind of done that. In fact, let me zoom out. There we go. If any of you would like to take a screenshot, well, this video will be on YouTube, so you can take a screenshot there if you like. But yeah, that's hopefully a roughly understandable overview of what's actually going on in these things. I'm going to come back. I'm going to stop sharing this and then come back. There we go. So that's why there are cases, if I'm not mistaken, where people have ended up with colostomy bags because their intestines have basically just stopped working. They've just completely died. It's not a coincidence once you see the way these things work. And the real problem for me is obesity and diabetes or any kind of metabolic syndrome is not caused by lack of GLP-1 drugs. They're caused by what you put in your mouth. This should not be a surprise to anyone. And yet, people don't seem to respond to me when I say, is it caused by a lack of GLP-1 drugs? Because they know it's not. And the problem is, if you don't provide education for your patient, they can take these drugs. Yes, of course, they will lose weight because it will basically it'll put you into starvation. So you lose muscle, you lose fat, and you lose bone. And I have a video coming soon of that where I go into the actual scientific evidence to show that too. But if you do that, yes, you will lose weight. But then once you've reached your target weight and you stop taking the drug, what do you think is going to happen? If you've not changed your habit, you're just going to go end up in this exact same way again. The critical thing with weight loss is education. It has to be. How can we maintain the health of our patients without actually educating them in what the right thing to do is? What are you going to do? Give them the drug, make them lose weight, they go home afterwards, put the weight back on, and then keep coming back in. That's not sustainable. That's ridiculous. And so if we give them the right education and we talk about the way carbohydrates incite insulin increase in the bloodstream relative to glucagon, that then puts them into a kind of storage mode, if you like, again, without being too technical. And therein lies the cause. If we show them that there are ways of eating which are low carbohydrate to no carbohydrate, like myself and many of you here, then it's not really possible to get fat or stay fat, because you're not inciting the insulin to glucagon ratio increase often enough to get into a state of metabolic syndrome, let alone obesity. And so these drugs, I'll be honest, I've used them 4 times for patients, and the reason is they were so big I thought, if I don't do something, you're going to die. That's an extreme situation. That, I think, is the only acceptable situation where these drugs can be used or should be used, because the risk of dying is worse than the risk of inhibiting peristalsis and what that can do to someone. But you see the lawsuits, I'm not going to go through them here, but take 30 seconds to Google. You see a large number of lawsuits of the problems that these drugs have caused. And what do you expect when it puts you into essentially a metabolic state of starvation because it stops you eating? What do you think is going to happen? Do you think not eating is healthy? It's absolutely absurd. I know some people will say, I've used them to good effect, the patient's doing great. Are they though? Are they really? Is that cell function going to come back that you've lost? Have you done DEXA scans to figure out whether they've lost muscle and bone? If you say you're treating diabetes with this, tell me how diabetes is caused by a lack of GLP-1 drugs, because it's not. And if it isn't, then you're not treating it, you're covering up the symptoms. Diabetes is caused by what you put in your mouth. To keep people putting the same thing into their mouths while then giving them drugs is just absurd. It's like sending someone to drug rehab while still supplying them with whatever drug it is they went into rehab for in the first place. I don't understand how this is not common sense to people. But yeah, I'm going off on a rant here, but let me just check for questions. I'm sure there's a few. No, that's good. Okay, that's a good sign. It means that I've explained everything. So Jimmy says, this makes so much sense why my local gastroenterologists are starting to refuse to do colonoscopies on those using GLP-1s for weight loss because of the bowel function issues. Yeah, because it's just stopping things working. And we like a Dr. Ab's rant. Thank you, Mark. But remember, there's 2 other receptors. There's GIP and there's glucagon receptors as well. I will talk about those in future videos as well. And the reason it's important to go through that is because some people will say one drug is better than another. Some people will say, oh, this new one called Retatrutide looks like it's so much better than the others. Is it though? Is it really? Because if you look at all the receptors that it's hitting and you understand how all of them work and what they're actually doing to your cells, would you want that for yourself? I'm not sure many people would. So I will go through the other receptors as well. Maybe we can make it like a 3-part series. And then we can hopefully share the education. I know this will be going on YouTube. If there's any other final questions, do pop them in the chat. I think that is everything though. Yep, it is. If you're watching this on YouTube and you'd like to take part in things like this and learn things like this, feel free to check out my online school, link in the description below. But I will see you guys in a few days' time for the next call. Have a good one.